All right, I know some of you are not excited about this, but it's time for the math. Okay, so some concentration calculations. First, let's review some basics. So concentration is the amount of the substance dissolved in a liquid. Okay, so we have dilute versus concentrated. Like this, dilute versus concentrated. We can find the concentration units on the front of your reference table, table D. So which expression could represent the concentration of a solution? Well, it's this one. We say it molar, refer to it as molarity. Parts per million is used to express. Here you can see just to visualize it, the difference between 5 parts per million, okay, and then increasing the number of parts per million. So it's concentration. The molarity of a solution is equal to moles per liter. It's important to remember liters because you can't use milliliters. Remember, we have unsaturated, saturated, and supersaturated. Saturated, maximum solute. Unsaturated, more could dissolve. Supersaturated, we made it by using heat, right? Because it actually has more solute. It's unstable. We'll get crystals. So remember, you form it by getting a solution, heating it, adding more and more and more solute, and then cooling it slowly. A seed crystal will cause that extra solute to just spill out. Now it's time for some calculations. So first, parts per million. Okay, are you ready? All right, so let's do this problem. A solution is prepared using 0.125 grams of glucose and enough water to make 250 grams of total solution. The concentration of the solution in parts per million. All right, so I need this formula, parts per million. Okay, so I'm just gonna do it like this so I can still see the formula. All right, so ppm equals, so the mass of the part. Okay, essentially it tells us is the mass of the solute. So the solute is the thing you are putting in. So that's got to be the smaller number. And on the bottom is the mass of the solution. It tells me that it is 250 grams. And then I have to do times a million. I can't forget that. A lot of people forget this. Don't forget. So now I just need calculator, right? So let's turn this on, and all we need to do is 0.125 divided by 250 equals times 1,000,000 equals 500. So 500 ppm. Now, when you look at my answer choices, I don't see 500. It's all in scientific notation. So how do I put this into scientific notation? Well, I want one digit here. Okay. It's going to be times 10 to the something ppm. So what? Well, where was the decimal here? It was at the end. Every number, no matter what, if it doesn't have a decimal, it's assumed to be there. I needed the decimal moved right here, right? Like this. So how many places did I move it? 1, 2. So this is the second. And it's positive because I moved the decimal to the left. So that means it goes left up. Or I can also think about it, 500 is really bigger than 5. So I need that to be a positive exponent. Right? So you should be able to figure out what the answer is now, right? So there we go. There's the answer. Okay, so by looking at this question, I can see all the answers say ppm. So I know I'm going to be using the parts per million concentration formula. So I know ppm, to write it in shorthand, is solute over solution times a million. All right, so I need the solute. solute. Well, the solute is that AgCl, but I'm gonna go down here for a moment. It says 1.2 times 10 to the negative 3 grams. Now, I could use exponents on the calculator. Personally, I'm just going to take it out of scientific notation. All right, so when I take it out of scientific notation, I need to move the decimal 3 places, and since it's negative, I need to go this way. I need to make the number smaller. So 1, 2, 3. So see, 1, 2, 3. Fill these spaces with zeros. So 0.0012. All right, so that is going to go for my solute, 0.0012, divided by, it says 800 grams of solution times a million. Remember, don't forget the times a million. So let's turn this on, and you need to do 0.0012 divided by 800 times 1, 6 zeros, 1, 2, 3, 4, 5, 6, equals 1.5. My units, ppm. And voila, there's the answer. All right, so again, another question. Look at my answer choices. They're all in ppm, parts per million. So I know I'm using this formula. Again, I have this, 8.5 times 10 to the negative 3. I'm going to prefer, my preference is just take it out of scientific notation, move the decimal 3 places, negative, go this way, 1, 2, 3, decimal, fill in spaces with zeros. So 0.0085. Okay. So I have an aqueous solution that has a mass of 490 grams, 8.5 times 10 to the negative 3 calcium ions. All right. So this is going to be the mass of the solute. The mass of the solution will be 490 times, please do not forget, times a million. Let's plug this into the calculator, okay? So 0.0085 divided by 490 times 1 million. That's 1 with 1, 2, 3, 4, 5, 6 zeros equals 17.34693878 ppm. Now I definitely have to round that, so I'm going to look at my answer choices. And do you see what we came up with? There's the answer. Okay, so scanning the question really quickly, I can see literally that it says parts per million. So I know I need this formula. So what is the total mass of solute in 1,000 grams of solution having a concentration of 5 parts per million? So here's my formula. The 5 parts per million goes in place of the parts per million. What else do I know? 1,000 grams of a solution. Well, obviously that goes for mass of solution. So what I'm trying to find is this. But what I cannot forget is times a million. I don't want to ever leave that out. Okay, so what I'm going to do is combine these like terms on this side. So I'm going to end up with 5 ppm on this side. Okay, and I think about this like over 1, so I'm going to just combine these into one term. So I'm going to get a million x over 1,000 grams. Okay, so now what? Well, I could simplify it on this side. Let's do that. Let's do a million divided by 1,000. See, 1, 6 zeros, 1, 2, 3, 4, 5, 6, divided by 1 with 3 zeros, 1,000x. So I have 5 parts per million equals 1,000x.
How do I get X by itself? Well, I am going to divide both sides by 1,000. That eliminates this. Okay, so 5 divided by 1,000 equals 0.005 grams, because that's what I was finding. Hopefully, looks like that on the answer. Do you see the option now? There's our answer. Okay, now let's look at molarity, right? So moles of solute over liters of solution. Must be in liters, okay? Don't forget this mole chart that you were given before. We're looking at this little section. Moles to liters using molarity, or liters to moles using molarity. Okay, so what is the molarity? All right, so molarity. There we go, this formula. That's what we're working with now. 2 liters, so I have moles on the top, liters on the bottom. So moles 0.50. This is about as straightforward as it gets, divided by 2.0 liters. So this is moles divided by liters. Now I do this math, and I get 0.50 divided by 2.0 equals 0.25 moles per liter, or 0.25 molar with a capital M. And hopefully that looks like an answer. And there's our answer. Okay, so again, we're continuing with our molarity formula. Okay, so what is the molarity of, and in order to use this formula, I need moles and liters. Now this question tries to trick you because it says 0.20 moles, but then it also gives me the gram formula mass. So that would lead me to believe at first that I need to convert it into grams, but I do not, because look at this formula, moles. So I just do moles, 0.20 moles divided by 0.50 liters. And I get my calculator so that I can do that math. 0.2 divided by 0.5 equals 0.4 moles per liter, or 0.4 molar, and hopefully that's an answer. Ta-da! There's the answer. All right, again, we are continuing with this formula. It says, what is the concentration that has 1.5 moles? But look at this. It says 500 milliliters. Look what this formula says I need, liters. That means I need to convert this into liters. So, like Beyonce says, in a box to the left, okay, and to go from milli to liters, I need to move 3 places. This has a decimal point, so that makes it easy peasy. 1, 2, 3. So 0.500 liters. Had to do that first. Now I can use that in my formula. Moles, 1.5 moles divided by 0.500 liters. So again, if I hadn't converted this first, I would definitely have gotten the wrong answer. So 1.5 divided by 0.500 equals 3 moles per liter, or 3 molar with a capital M. And hopefully that answer is there. We did the work. Now there's the answer. Okay, this question uses this formula, but kind of in a weird way. It says, which one of these samples has the greatest number of moles? Okay, so I have a molarity and I have a liters, but I want to find moles. So ideally what I'm going to do is just rearrange this formula. So if I multiply both sides of these by liters, so if I took molarity equals moles divided by liters. Okay, do you see that? All right. I'm trying to solve for moles. So let's just do this. Let's multiply both sides by liters. So what I will get is liters times molarity equals moles. Why? Because these cancel out. Does that make sense? Now I'm going to use this to check. So the first option, I have 1 liter times 2 molar. That's 2 moles. I have 2 liters times 2 molar is 4 moles. I have 4 liters times 0.50 molar is, you know what that is? I'm pretty sure that's 2, but I'm not trusting myself right now. So let's just double check. 4 times 0.5 is 2 moles. Well, I know that's wrong because I have 2 answers now that are 2. And then 3 times 0.50 is 1.5 moles. So now, easy peasy, should be able to figure out which one has the greatest number of moles. We figured it out. There's the answer. Again, still using this formula. Now, how many moles have to be dissolved to make? All right, so what do I know? Molarity, 2.0 m equals. Moles is what I'm trying to find. I have 1.5 liters. Okay. Now, there are a few strategies. One that students seem to be comfortable with is putting this over 1 and doing cross multiplying. Okay, so I'm going to model that one this way. Okay, so I'm going to take 2.0 molar times 1.5 liters equals, well, 1 times mole is just mole. So now I need to multiply those together, and so I do 2.0 times 1.5 equals 3 moles. Okay, and then hopefully that's an answer. There we have it. There's our answer. Okay, now we're going to move on to percent composition. Formula from the back of your reference table. Okay, this one is kind of easy because it's just a numerical setup question. And I need to use this formula for percent composition. So it's mass of part over mass of whole times 100. So I need to know the part divided by the whole and then times 100. Reason I want to write it out is because you have to be careful of something. When you're talking about a solution, the mass of the part is going to be the solute, and the mass of the whole thing is going to be the solution, and then it's times 100. Now, what if you forget which way it needs to go? Just use parts per million as a guide, okay? But we're talking about percent composition. So I can see that I have 25 grams of KNO3. So that's easy. That's the mass of the solute. What you have to remember is that the solution, the answer, is made up of 2 things. It is the solute and it is also the solvent. Now, sometimes it just says mass of solution, easy peasy. In this case, it doesn't. It doesn't say 200 grams of solution. It says 200 grams of H2O, of water. So in order to find the mass of the solution, I need 25 plus 200. And then I can't forget times 100. And then hopefully we see that answer there. Ta-da! There it is. Okay, this one again is just showing a numerical setup for percent mass. So we're going to use this formula, mass of part over mass of whole times 100. And remember, when we're talking solutions, that's solute over solution times 100. So that's the percent. So what's my solute? Well, KNO3 is being dissolved, so that's 70. What's my solution? 70 plus 100 and then multiplied by 100. Since I only need to show correct numerical setup, this is it. What would also be okay? 70.0 divided by 170 times 100. You cannot leave off the times 100. Don't forget. Okay, this is a whole lot to process. Okay, so our question says determine the maximum volume of 2 propanol in the 132 milliliter sample. So let's try and see what information I have. Okay, so I have a 132 milliliter sample. All right, and I know I'm looking, okay, so as soon as given a 132 milliliter sample of 91% aqueous 2-propanol. Okay, so it's giving me the solution and a percent and asking me for the solute. So again, to set it up for a solution, solute over solution times 100. So I know my percent, 91, right, equals, solute is what I'm trying to find. My solution is 132 milliliters times 100. Okay, let's simplify this side. So 91 equals 100x over 132 milliliters. Okay, so now what? I need to solve for x, right? So what I could do here is just do 132 milliliters over 100. So do you see that? Which allows me to cross this out, cross this out, cross this out, cross this out. But if I do that on that side, I have to do it on this side. So 132 over 100. So this 91 is really over 1, right? So I'm going to multiply these two. So I'm going to start there. 132 times 91 equals 12012 divided by 100 divided by 100 equals 120.12 milliliters. Now, let's see. Does that make sense? Well, it's 91%. That's a lot, right? And I started with 132 milliliters. Doesn't make sense that 120 of it would be the propanol? Yes, absolutely. Because that's pretty close to this number, but not over it. Like if I got an answer that was 500 milliliters, that would make no sense because I only have 132 to start with. So there you go. That's how to set it up when you're using the percent composition that way. Okay, again, whew, a whole lot of reading. All right, so let's just go to the question. So one engine cooling system has a volume, okay, of 6,400 milliliters. Determine the volume of ethylene glycol. So I'm talking about antifreeze. So ethylene glycol, that's the solute, okay? In the completely filled engine cooling system, when the concentration of ethylene glycol is 50% by volume. So I'm using this formula and a similar setup. Let's see if I can figure it out. So I know 50 is my percent. The mass of the part is the solute, and that's what I don't know. The mass of the whole thing, okay, or the volume of the whole thing, milliliters, times 100. Okay, again, similarly to what I did before, let's combine those terms. 100x over 6,400 milliliters. Okay, I want x by itself, so I could multiply by 6,400 milliliters over 100. Do that on both sides. 6,400 milliliters over 100. This is over 1 just to give reference of where it is. So 100 crosses out, 6,400 milliliters crosses out. So over here, all I need to do is 6,400 times 50 and then divide it by 100. So let's do that. 6,400 times 50 divided by 100 equals 3,200 milliliters. Which literally should make brilliant sense. So if the concentration is 50% by volume and the whole volume is this, 50% of it should be this. My answer literally makes beautiful sense. And there we have it. A whole bunch, but that was concentration calculations.